Hello, everyone. I want to welcome you back to our lecture series. Today we'll be talking about temperature and density. Let's get started. At the end of this lecture, there are a few things we would like to get. Number one, we're able to know how to calculate the density of objects from its given mass and volume. We use density to calculate the mass or volume of an object by the factor unit or formula method. I recommend the factor unit method, which we call the dimensional analysis. And then we'll be able to calculate the specific gravity of a given object, the specific gravity comparing the gravity, the density of any object to that of the density of water. And then we're able to recognize different temperature scales, common temperature scales, and finally, we're able to convert one temperature unit to another. So these are our learning objective. Let's get it started. Of course, the word temperature, if you live in this part of the world, which is the Pacific Northwest, is something that you use every day, particularly when you wake up in the morning in winter or in early spring. Temperature changes a lot. So temperature simply measures the degree of hotness or coldness of a body, to put it simply. We wake up in the morning and say how hot it is or how cold it is. So it offers us both some qualitative measurement, which is hotness or coldness, and then the actual numbers, which is the quantitative measurement of temperature. So temperature is measured in common units, and a few of them we're going to be highlighting in this lecture. They include the Fahrenheit, the Celsius, and the Kelvin scale. The Celsius and the Kelvin scale are the ones used mainly in scientific work. And in other parts of the world, apart from maybe US and a few other places, the Celsius scale is the one commonly used. These three temperature scales are shown in this graphic below. The first one is the Fahrenheit, that has a boiling point of 212 Fahrenheit and a melting point of 32 degrees Fahrenheit. And if you measure the interval between those two, that's going to give you about 180. So the Fahrenheit scale is commonly used around here in the USA to measure temperature. We have the negative 459 degree Fahrenheit is the absolute zero, which is a theoretical temperature. At that temperature, the volume of everything is just expected to be zero. So it's a more or less a theoretical temperature. And I'm not going to be offering any more insight on that because it is not relevant to what we're going to be talking about. Now we go to the Celsius temperature. The Celsius or the centigrade temperature scale has a boiling point of 100 and a melting point of 0 degree Celsius, and then it has an absolute zero temperature of negative 273 degrees Celsius. And then the Kelvin temperature, on the other hand, which is commonly used in scientific work a lot, particularly in studying gases, has a boiling point of 373 Kelvin and a melting point or freezing point of 273 Kelvin. Now, this does not usually have a degree written before it. It usually doesn't have like the degree. So if you want to write 5 Kelvin, you just say 5 Kelvin. You don't say degree. You don't say degree Kelvin. You just say Kelvin. Okay? So that is how you write the Kelvin temperature scale. Okay. And then, so these are the three common temperature scales we'll be talking about in this class, and those are the ones we're going to be doing those interconversions. All right. So why do we even have to talk about temperature? We have to talk about temperature because particularly this class is centered towards allied health and allied health mainly, and a couple of other agricultural students that are here. But it's important we talk about what's the relevance of why do we even study temperature in the first place. That has a very direct application. We know that the normal body temperature, of course, the temperature of the body at which all the organs will function optimally and all enzymes will be active without being denatured, is 98 degrees Fahrenheit or 37 degrees Celsius. So the body hormones, the body enzymes and organs function at the optimal temperature. So any change in this temperature could be a sign of disease, of an infection, of a pathogenesis or something wrong. So there are a few important terms that are usually used commonly in the health sciences that we're going to be bringing out from this. Number one, a person is considered to be febrile, the word febrile, or paraxial body temperature. When the body temperature exceeds 38 degrees Celsius, the person is defined to be febrile or paraxial because the body temperature has increased to 38 degrees. In this case, we call it a little bit of mild fever. Now, but when it goes beyond that, it becomes hyperexia. Is that febrile state when the temperature exceeds 41 degrees Celsius? In this place, the person is having a very serious fever, and that could be some signs of disease, infection, or something going on with the person. And on the hand, when the body temperature drops very much, particularly if you stay outside in the winter for a long time, in a football game or baseball game in the winter, we use the word hypothermia. It's a term used when the body temperature abnormally drops below 35 degrees Celsius on 5 degrees Fahrenheit. So that could lead to a couple of stuff like frostbite can happen and a lot of them. So assessment of body temperature is used in the determination of the following. Number one, nursing care. So if the person, I have kids at home, and at times one of the ways I know they're sick is when I look at their body temperature, it goes high. So then again, medical diagnosis, what is wrong with them, treatment, and finally, laboratory test. So I've listed a few instruments that are used. These are electronic thermometers that are commonly used in the medical field to check or to measure the temperature. I have one of these at home. You point this one particularly. This is the one I have. Point it at the forehead, and it measures that, and you can change it between the centigrade or Celsius scale and the Kelvin scale. So these are some importance of temperature in health, and it's important that we know that when we are teaching you, we're trying to impart an important skill in you that is going to be applied just beyond the classroom. Let's now go to the crux of the matter. Temperature conversions. How do we convert from one temperature to another? That's what we're going to be doing here. Now, to convert from one temperature to another, we use the temperature conversion formulas, and there are 4 of them. You are not expected at this point to begin to memorize these. These are going to be provided for you in the exams. Now, but it will be your responsibility to know which one to use and how to plug it in. So the first one is that if we're going from Fahrenheit to Celsius, right, we're looking for Celsius. So the Celsius formula will be 509 bracket, the temperature given in Fahrenheit minus 32, close bracket. You just need to plug it in. You don't need to do anything. Just plug it in, do the arithmetic, and write your answer. In the second one, if you're converting from Celsius to Fahrenheit, what it means is that you have your Celsius, you're looking for Fahrenheit. It will be 9/5 multiplied by the Celsius temperature scale plus 32. You have to do these two before you add the 32 to get your answer correctly. The last two is converting from Kelvin to Celsius, which you subtract. If you have it in Celsius, you subtract the Kelvin temperature. You subtract the Kelvin 273 from the Kelvin temperature. And if you're converting to Celsius and from Celsius to Kelvin, what do? You have the Kelvin temperature. What you need to do is to add 273 to the Celsius temperature to get the Kelvin temperature. So these are the things you need to do. So it's important. So these formulas, I'm going to provide them for you, but I'm going to do just about 2 reflection problems to tell you how this is done. Let's get to it. So tonight's low in Yakima is going to be 43 degrees Fahrenheit. So what is the temperature in what? In Celsius and in Kelvin. So we're going to use one stone to kill 2 birds. So the first one we're going to start is that we have a temperature in Fahrenheit given, and we're looking for it in Celsius. So what do? We're going to use the appropriate formula. The formulas have been given to you. So what you need to do is just to put the formula. The right formula to use here is the Celsius temperature, then 5/9 bracket, degree Fahrenheit minus 32. Minus 32. So what I'm going to do next is to plug it in. I'll just plug it in. So it's going to be 5/9 bracket. The temperature I have is 43 degrees Fahrenheit minus 32. And if I subtract 32 from 43 and multiply it by 5/9, I'm going to get about 6.1 degrees Celsius. That's what I get. And then since I'm in Celsius now, and I want to go in Kelvin, which is the second question, that's an easy thing to do. What I simply need to do is to add 273 from the formula. The formula is degrees Celsius plus 273. So if I have my 6.1 degrees Celsius, I add 273 to it, and that gives me about 279 Kelvin temperature. So that is how so this is very straightforward and direct. There's nothing tricky about it. And just what you need to do is to figure out which particular formula to use, and you plug it in and you get your answer. So we'll go to the next one. Oh, we jump to the reflection question 2. It says tonight's temperature at the center of the South Pole is going to be negative 53.5 degrees Celsius. What is the temperature in Kelvin and in Fahrenheit? That's what it's asking. So let's do it quickly. Again, there are 2 questions here. We have it in Celsius. We wanna give it first in Kelvin. So let's do it in Kelvin. In Kelvin, what do we do? If you wanna convert it to Kelvin and you wanna use the formula, what formula do you use? You have it in Celsius rather, and you wanna convert it to Kelvin. What you simply need to do is the Celsius or the centigrade scale plus 273. If we did that, we're gonna now add our temperature, which is negative 53.5 plus 273, and when you do that, you're going to get 219.5 Kelvin. Now, for the second part, since I have it already, no, Celsius, not Kelvin, remember that this is in Celsius, sorry. Well, yes, we're correct. This is Kelvin. We're very correct. So we're looking for the answer in Kelvin, and we have it in Kelvin temperature scale. Now, the next question will be, we were given the centigrade or the Celsius scale, but we want to convert it to the Fahrenheit. We're going to have to go back to the formula. So the formula to convert it, the Fahrenheit formula is equal to 9/5 bracket degree Celsius. You have to multiply the value of the temperature in Celsius to 9/5 before you're adding your 32. If you don't do it like that, you're going to get the wrong answer. So let's do it. It's going to be 9 divided by 5 times negative 53. So first, I'm doing negative 53.5 times 9/5. Then whatever answer I get, I add it plus 32. And if you did that correctly, you're going to get negative 64.3 degrees Fahrenheit. This becomes your final answer, or our final answer. Again, we got this one here too as well. So as you're watching these videos, you can easily pause these videos, try out yourself, see what the answer is before you get to the end to see what the final answer I got, and also practice with your worksheet as well. And having done this, we're now going to be switching gears to the next topic, which is the big elephant in the room, density. Density is the ratio of mass to volume, is mass per unit volume of any object. It actually measures both the size of the object and thickness of the object, because volume measures the thickness of object. So there is just comparing the relative mass of an object, comparing the relative mass of an object to its volume. That's basically what the information on density gives us. So density formula is mass over volume, where D represents the density, M is the mass, and V is the volume. So there are a lot of units. Every density just has both the mass on top and the volume unit. So any mass over volume unit is going to work for it. However, these following units are commonly used. The commonly used units are the grams per mil are used for liquid and solid, and then the grams per liter are usually used for gases, and a couple of other units. So you can decide to say, okay, if your density, if you want to measure yours, if you have it in kilogram and you have it in feet squared, it doesn't, feet cubed, it doesn't matter. It can be in any unit. All right. So far, what you have on top is mass, and what you have below is volume. So let's see an example here. It says, example, 25.4 ml of a liquid has a mass of this. What is the density in grams per ml? Of course, we don't have to change anything because we have grams and we have mil. So what you simply need to do is to write the formula D. I want to write the capital D is mass over volume. You put your mass. The mass is this, 78.5 grams. This is 75 grams divided by 25.4 mil. And when you do that math correctly, it's going to give you about 3.09 grams per mil. And if you look at it, the density itself has two units, grams on top, mils below, or the mass, the mass unit on top, the volume density below. What it means is that density itself can be used as a conversion factor. So density can be used as a conversion factor because it has units. Because it has 2 units. And that will actually form the crux of what we're going to be doing in other solutions. Let's take it from there. Let's introduce a new term, the specific gravity. Specific gravity simply means comparing the density of any object to the density of water. That's what this is all about. So it simply is the density of a substance in same unit over the density of water. So the unit on top must be the same thing with the unit below so that both unit cancels. And when both unit cancels, there is no unit. So the specific gravity is a ratio of 2 densities to the same unit, and therefore it has no unit because the unit cancel out. When we do this in the lab, a lot of students get into the temptation of trying to give me a unit. And they say the unit is SG. SG simply means specific gravity. It just simply has no unit. Let's see an example here. The density of silver is about 10.5 grams per mole, and that of water is 1.00 grams per mole. It says, what is the specific gravity? The specific gravity simply is SG will be the density of silver. So I'll write it, density of silver over density of water. That my D is looking wonky. I'm going to write it density of water. And then when you plug that in, it's going to be 10.5 grams per mole over 1.00 grams per mole. And when you cancel both, let's try to cancel this, we cancel this, your answer becomes just 10 point, because this is 1, 10.5. So the specific gravity of silver is 10.5. And there is no unit because both units cancel, both the upper unit and the lower unit cancel out. Let's now begin to solve some problems here. Yes, it says, let's solve this problem. This is an interesting one. It says 35.0 ml of a sample of liquid is put in an empty beaker that has a mass. So the mass of the beaker, let's try to record something. So the volume of this sample of liquid is that, liquid will take the volume of the container. So that's the volume. Then it says the mass of the beaker, the mass of the empty beaker, let's put it here. Let's try to write out what we have. Mass of empty beaker. It's important you get the information given when you're solving problems is 44.3 grams. It now says the mass of beaker and the containing liquid. So when you put when the liquid was put into the beaker, it was weighed again. The mass came up to 61.8. So here I'm going to say mass of beaker plus liquid. That gave me 61.8 grams. Then what will be, remember, density itself simply means the mass of the object over the volume of the object, not the mass within the mass of objects. It has to be individual. So but in this case, we don't have the mass of the liquid, but we can do a little bit of arithmetic here to find the mass of what? The liquid. What do? If we subtract 44.3 minus this, that gives us only the liquid part. So the mass of liquid will now be 61.8, which is the mass of both of them, minus 44.3, the empty container. So what is left for us will be 17.5 grams, which is the mass of the liquid. So what do we now need to do this? We need two stuff. We have the volume of the liquid, we have the mass of the liquid, and then we begin to apply our density. So our density will now be mass over volume, and the mass will be 17.5 grams divided by 35.0 mils. And if you divide both those two, it's going to give you about 0.5 grams per mil. So if you want to maintain the amount of digits in this, which we usually don't do here, you can just say 0.500 grams per mil to maintain the 3 number of digits, because this is 3 on top, this is 3. But remember, we said in this class, significant digits is not being enforced. But once in a while, I try to plug that in just to let you know, because it's something that we expect that you need to know at this point. All right. We'll now go to the next question. Again, practice makes perfect. I try to bring in as many questions as possible. It says the density of a metal has been determined to be 7.20 grams per mil. It says use the density value to calculate the mass of the sample. Right? Remember what I said. Density is a conversion factor. Remember, what it simply means here is that this density, we can write that 77.20 grams is equal to 1 mil. And if we want to generate 2 factors, there are 2 factors we can generate here. What are the 2 factors? We can say 7.20 grams over 1 mil, or we can say 1 mil over 7.20 grams. And what we're going to be using would determine what we want to find. So what are we looking for? We're looking for the first one. It says use this density value, which is this, to calculate the mass. So we want the one that has the mass on top, the grams. That's what we're going to be using. So if we bring that here, we're gonna start with what we're given, 43.0 mil. Of course, if you use that one, 7.20 grams over 1 mil. The mil, we cancel the mil, and then when you multiply these two, you're gonna get 309.6 grams. So that's what you get. 309.6 grams will be the mass of that ion, because this is the iron metal. The iron metal has a density of this. So the mass of the iron metal that will occupy a volume of 43 mils will be 309.6 grams. Or approximately, you can say it is 310 grams. Then the second one is use the same density value of this iron metal to calculate the volume occupied by 129 grams of iron. So what are we going to do? We start from the mass we were given again. We'll now look for the conversion factor. Since we're looking for the mils, right? The volume, we're going to use this conversion factor. So what we're simply going to do is 1 mil on top and then 7.20 grams. This will cancel this. So when you divide 129 over 7.2, you're going to get about 17.9 mils or milliliters of iron will occupy the space of the mass of 129 grams of iron. All right. We now go to another important thing. So in this question, I'm demonstrating 2 things. We're going to calculate the density of an irregular object. And an irregular object does not have a definite volume, because a definite volume, if something is a rectangle, you say length times width times height, right? If it is oval, you use the oval formula to calculate the volume when you know the radius. But in this case, it is an irregular object. So what are we going to do? How do we first of all determine the volume? The question says an irregular piece of precious metal weighs 15.7 grams. It was then placed in a graduated cylinder that contains some water. It says it does not float. Now, for this to take place, it is not supposed to float. If it is floating, that means there's going to be a problem. For this thing to hold through, the object does not have to float. It has to sink inside the water for this to hold through. It says water in the cylinder was at this level before it was added, and at this level after it was added. It says what is the density of the metal. So let's try to get out the information that we're given here. So what do we do first? The first thing we do here is know the information that we're given. So first of all, the mass of the precious metal, let's write it down. M is equal to, let's write it down, 15.7 grams. Then the next thing, it says it was then placed into the graduated cylinder, right, that contains some water. And it does not, it says water in the cylinder before it was added. So before it was added, which we call V1. So before I do that, let me explain this graphic for you now. So this graphic actually shows you what we call the determination of density by water displacement, or rather the determination of volume by water displacement. So look at what happened here. So first of all, initially, when water was placed inside this particular cylinder, this graduated cylinder, the volume was measured to be V1, right? And then the block or the metal was added. And look at what happens in the second image. This is the first image. In the second image here to the right, look at what happened. The water level rose from V1 to V2, which is the new volume. Because this particular solid has taken some space inside this graduated cylinder to push up this volume to this V2. Now, to determine the volume of this block, what are we going to do? It's just to subtract the first volume, the initial volume, which is only before the metal was added, from the second volume, which is when the metal has been added. So in this case, the volume of this metal will be the amount of water it has displaced, which is V2 minus V1. So that's what we're going to do. So here V1, our V1 is going to be, before the water was added, was 31.6 mils. And then before the metal was added. So then after adding the metal, what happens? It rose to 36.3 mils. Then what means is that the volume of this particular metal will be, because it's irregular, we cannot calculate. It's not a square. It's not a sphere. It's not a block or a square. So we have to use this method. So the volume will be to subtract the first volume from the second volume, which will be 36.3 mils minus 31.6 mils. And when you do your calculation, right, you're going to get about 4.7 mils. So what it means is that we now have the mass of this object. We now have the mass of the object, and we have the volume. And now to punch it in, density itself will be mass over volume. And the mass is about 15.7 grams on top, and the volume is 4.7 mils below. And when you do the calculation correctly, you're going to get about 3.3 grams per mil. That becomes your final answer. Easy cheesy. All right, we go to the next problem. In this problem, it says an object has a mass of 2.70 kilogram and a volume of 1.50 quart. It says, what is the density of this object in grams per mil? Look at what happens. It gives the mass in kilogram, but now it wants it in gram. It gave the volume in quart, now it wants it in mils. The second question becomes the second part. Will this object float on water if the density of water is 1.00 grams per mil? You see that? So if this object has a density that is greater than 1.0, it's not going to float in water. But if it is less than 1.00, which is grams per mil, which is the density of water, it will float. So that's what we're going to determine. And we're given the following conversion factor. 1 quart is equal to 0.496 mil. So let's start. So what are we going to do? To solve this problem systematically, what we're going to do is first, we're going to convert this guy to gram, which is easy to do. We know that 1 kilogram is equivalent to 1,000 grams. If we know that, what we need to do is to 2.07 kilogram. We say, we put the kilogram down, we want it to be gone, we put the 1,000 grams on top. And when you multiply it, it's going to give you 2,700 grams. Or, if you want to do this, 2.7 times 10 to the power of 3 grams. It doesn't matter how you express it. For the second one, we want to convert 1.50 quarts to mils, not to liters. We're given to milliliters. But you know, we can always take it from there. Remember that a liter is 1,000 mils. So if we have that going for us, let's do something with that. So we're going to start with 1.50 quarts. To take away quart, we're using this. So we're going to take away quart. 1 quart will be down, and then we're going to have 0.946 liters here. So look at what happens. We start cancelling out immediately. Remember, this was cancelled out. Don't forget that. And then the next thing we're going to do is we want it to be in mils, not in liters. So we know that we're not going to use this one. So we know that a liter, we'll put it down to cancel, is equivalent to 1,000 mils. If this cancels this, we plug everything in the calculator, we're going to get about 1419 mils. This becomes our answer. Now, we've converted the kilogram to grams. Remember that? And we've converted the quart to mils. So now we can easily do our density. Our density will now be, remember, the density will now be, if I move this a little bit up, well, let's see. If I move my canvas a little bit up here, but I don't want to move away from the question completely. It's going to be, so our density will now be equal to mass over volume. And if we plugged everything in 2700 over 1419, that, of course, this will be grams, this will be mils. And if you do the math correctly, it's going to give you about 1.90 grams. 1.90 grams per mil of 1.90 grams per mil will be the density of that object. Now, the second question says, let me try to highlight this. It says, will this object float on water if the density of water is 1.00 grams per mil? Now look at this. The density of this object is greater than the density of water, which is 1.00 grams per mil. Therefore, this object will not float in water. This object will not float in water because the density of this object, is greater than that of water, and it will not float. It will not float on water. It will not float on water. All right, that is how you solve that problem. Let's now quickly finish the last two problems here. It says, what is the mass of 8.1 centimeter cube of silver, or cubic centimeter, whatever we want to say it, of silver? If the density of silver is this, again, we're going to solve it the way we've solved others. We're going to start with what we're given. This time you are given this, so it's going to be 8.1 cubic centimeter, and you have this density. Remember, density is a conversion factor, so I'm going to put 1 cubic centimeter down, and then I'm going to put 10.5 grams up. This cancels this, and when you do 8.1 times 10.5, that's going to give you about 85.05 grams of silver. Now, and the last but not the least of this problem, again, it says, what is the volume of 18 kilogram of silver? What is the volume? Again, we know the density of silver is 10.5 grams per cubic centimeter. So what are we going to do? First of all, we want to convert this to what? Since we have to eliminate kilogram, so we have to convert this kilogram to grams. So let's start that. Of course, you know that a kilogram is equal to 1,000 grams. So if we start 18 kilogram, first of all, we'll convert it to what? Gram. So we know that a kilogram down, 1,000 gram up. This will cancel. And then we're now bringing the density. Remember, this simply means 10.5 grams over 1 cubic centimeter. Or we can say 1 cubic centimeter over 10.5 grams. So we'll plug this in quickly. So to plug it in, I would want to cancel our gram. And the one that has the grams, and to find the volume, what you simply need to do is to flip the density formula. That's what we're going to be doing. So we're going to put this on top, 1 cubic centimeter on top, and then we're going to put the grams down, 10.5 grams. And then the grams, we cancel the grams. And when you punch everything correctly into your calculator, you're going to get 1714 cubic centimeter. That becomes the density. Sorry, that becomes the volume of the silver that will have a mass of 18 kilogram. All right, and having said that, we've come to the end of this lecture. Thank you for listening. Bye.